So now we're going to talk about some determinants of some very special matrices, right? So the first theorem that we're going to show is that the determinant of a lower triangular matrix, or upper, is just the product of its diagonal entries. And for the proof, we're going to use a proof technique called the principle of mathematical induction. And the idea of induction is as follows. The first thing you do, right? So the idea is you wanna prove a bunch of different statements. So statement 1, statement 2, statement 3. You're actually proving statements that are indexed by the positive integers, right? So an infinite number of statements, right? You want to prove this. So how do we do that? How do we prove that? Well, here's one strategy that would work, right? So the first step, so stage 1, step 1, is prove S1. So prove the first one. Prove the first statement holds. So step 2 is assume S sub n for any n greater than or equal to 1, and prove, so, and then use it to prove Sn plus 1. So the idea is, and this, if you can do this, right, if you can perform step 1 and then step 2, right, so for any n, right, then you've proven this for all statements. And the idea works like a chain of dominoes, right? You set up all the dominoes so that if one tips, then it'll push another over, right? And then you just push the first one, right? If you push the first one, then all the rest of them have to fall. So here's the idea. So what's the determinant of a 1 by 1, right? So the first thing we're going to show is the determinant of 1 by 1 lower triangular matrix is the diagonal, right? Well, the determinant of a 1 by 1 matrix is just A11, and that's the only diagonal entry, so we've proven the first statement holds, right? So now suppose, so this is for any 1 by 1 matrix. Now suppose the determinant of A, where A is lower triangular, is equal to the product of the diagonal entries, of its diagonal entries. And suppose that's true for any n by n matrix A. Suppose that is true, right? So now we're on to step 2. We've taken care of S1, and now we're assuming Sn, which is this statement. Now we want to show that Sn plus 1 holds, right? Well, the determinant, right? So now let's suppose that B, so suppose B is n plus 1 by n plus 1. So the determinant of B is going to be equal to, well, we do the Laplace expansion, right? So it's B11 C11 plus B12 C12 plus, right? This is just the definition that we're working with right now. B1n C1n but it's lower triangular. It's lower triangular, so that means that this guy is 0, so it goes to 0, so we cancel him out. And all the rest of these guys are 0, and the only thing that'll remain is the B11. B11, and this will be the determinant of A11 by definition, right? Well, the determinant of A11, right? Well, A11 is an n by n matrix, right? And in particular, because B was lower triangular, A11, so this is for any n by n lower triangular, right? So we've assumed that for any lower triangular matrix that's n by n, this is going to be the product of the diagonal entries. But the diagonal entries of A11, because we just removed the first row and first column, are the diagonal entries of B after B11, right? And so this is equal to, in the long run, the product of the diagonal entries of B. And that's the proof. That's it. Pretty simple. And we can use this to actually calculate the determinants of our elementary matrices, which is kind of cool. So here's another theorem that tells us the determinants of our elementary matrices. Well, first of all, we have the determinant of Eij r. So when I remove r, or I add r of row I to row j, right? Well, that is going to be equal to 1. That's true. The determinant of Eij, right? I'm permuting, or I'm interchanging row I with row j, is actually equal to -1. This will be the toughest thing that we have to show. We'll have to do induction again. And the determinant of Ei of r is equal to r. So the proof of this is pretty quick. So first of all, Eij of r is diagonal. So Ei is not diagonal, rather, but lower triangular or upper triangular. Right? Because I does not equal j for all these guys, right? And so that r is going to be off of the diagonal, and it's either above the diagonal or below the diagonal. You can't be on the diagonal here. And all the diagonal entries are 1. So the diagonal entries are 1. So the determinant is also equal to 1, right? It's just the product, by our last theorem, it's just the product of all the entries there. Also, EIR is also lower triangular or upper, right? It's in particular, it's just diagonal. Well, it's both lower and upper triangular. So it's just the product of all the entries, and all the entries except for 1 are r on the diagonal, and so it's just r times a bunch of 1s, so the determinant is equal to r. So we've proven this guy, and we've proven this guy. This guy's going to take a little more effort, right? So we do induction, but now the induction is, well, in order to exchange something, I have to have at least 2 rows, so our induction starts off with the first exchange matrix, right? And the only exchange matrix in the 2x2 case is 0, 1, 1, 0. And the determinant here is going to be 0 times 0 minus 1 times 1 is equal to -1. So we've proven it for the 2x2 case. Now suppose that all n by n interchange matrices have determinant 1, or determinant -1. Well, so we just do a Laplace expansion for the n plus 1, right? So we check out determinant of Eij, where now we're assuming that Eij is an interchange where I have n plus 1 rows and n plus 1 columns. Well, that's equal to, I expand along one row that's not being interchanged, right? There has to be at least one row that's not being interchanged, because n plus 1 is going to be greater than 2, right? Because this was my first case, quote unquote, my first case. So I do that, and what am I going to get? I'm going to get some entry here, right? Well, actually, so if I so I'll get a 0 here. So let's say I expand upon the kth row, right? So the kth row is going to be Eij K1 determinant. So this will be CK1 plus all the way up to Eij of K n plus 1 ck n plus 1, right? But the only thing, because this is a permutation matrix and I'm expanding upon a row that's not I or j, then the only thing that's going to be a 1, everything else will be 0, is the kth entry, right? So I have, and that'll be a 1. So this will be, and in the long run, since I'm adding k to k and I have -1 to the 2k, that'll be 1. This will be determinant of Eij, but where I've removed the kth row and the kth column, right? But now this is also an interchange matrix, right? Because I have exactly, I'm replacing one row with another, right? So its determinant has to be equal to -1. And therefore we've proven it for the n plus 1 by n plus 1 case using the induction step. And that completes our proof.